Welcome to the lecture on the excitation due to support. So, here in this case, we have a system that is on a support, and support is vibrating. So, a frequent example is the earthquake. If there is some earthquake and there is a building, so the due to the earthquake motions, what will be the motion on the some particular floor, particular story building? So here also there are some cases like if we have some vibration on the ground and you have kept some machine, okay, so what is the vibration due to the ground, how much it is going to have the vibration on the top of the machine, or some instrument you are keeping on certain table and the table is vibrating, then your instrument is what is the vibration amplitude of the instrument. So there are these kind of examples. So here we will take a single degree of freedom system and that is on the support, okay. So when we say support means we say that it has some damping and some stiffness, so it could be the some like something kept on some elastomer, okay. So what is the vibration of this kind of system? So let's take this example. So we have this system consisting the mass element, stiffness element and damping element. Now if there is the motion of this support, so this has some motion y, harmonic excitation of the support. So y equal to y sin omega t. Okay. So due to the excitation of the support, what be the response of this mass? Let's say this is x. So what will be the x? And so we will write the equation of motion. So first we will make the free body diagram of this mass. So let's say we have this mass, okay, because this mass is, let's say, the direction of the acceleration of the mass, and this mass is compressing this spring, so this spring we will apply the force, but the net compression of the spring will be the difference between the x and y, okay. So the force that it will apply will be k x minus y, because this is moving x, this is moving y, so the net compression of the spring or stretch of the spring is x minus y. Similarly, the damper, the net velocity is x dot minus y dot. Now we can write the equations of motion applying the Newton's law. So sigma f equal to mx dot double dot. So here mx double dot equal to minus c x dot minus y dot minus k x minus y. So here we can write mx double dot plus cx dot plus kx equal to cy dot plus ky. Okay, so here we have minus cx dot, we bring it to the left side, so it is cx dot and this is kx, and plus cy dot and plus ky. Now we have y equal to y sin omega t and y dot equal to y omega into cos omega t. So here we can write c omega into y cos omega t plus k into y sin omega t. So we can write y into k sin omega t plus c omega cos omega t. Now we can write these two, the summation, the addition of the two harmonics of the same frequency. So the amplitude will be under root k square plus c omega square and this will be sin omega t plus some phase, let's say alpha, where tan alpha equal to c omega by k equal to 2 into zeta into r. Okay, where r equal to omega by omega n. So what we see that this equation is converted into a equation of forced vibration where the amplitude of force is this and this is the harmonic motion. Now the response x will be equal to x sin omega t plus alpha minus phi, where again the phi is the phase lag. It is the phase lag between this and the x. So what will be the x? So again we will compare this equation with the equation mx double dot plus cx dot plus kx equal to f0 sin omega t. So here what we see that in that case x equal to f0 upon k minus m omega square whole square plus c omega whole square under root. Here f0 is like y root k square plus c omega square. So we can write here y root k square plus c omega square upon root k minus m omega square whole square plus c omega whole square. So here we can write x by y equal to, so here we can write take k outside, so under root here is k 1 plus c omega by k whole square upon, again here we can take k outside, so it is under root 1 minus m omega square by k whole square plus c omega by k whole square. So this will cancel out. So we can write c omega by k as 2 zeta r. So here we can write under root 1 plus 2 zeta r whole square upon under root 1 minus r square whole square plus 2 zeta r whole square. So here we get x. So here x is x equal to the absolute amplitude of the mass. So because x equal to x sin omega t plus alpha minus phi, it represents the absolute motion of the mass. Now here the phase lag equal to phi minus alpha. So that is equal to, and here phi here tan phi is 2 zeta r upon 1 minus r square. So here phi equal to tan inverse 2 zeta r upon 1 minus r square minus alpha, and alpha is here tan inverse 2 zeta r. So this is the phase lag. Now we take the case when r is much less than 1. So when r is much less than 1, x by y is tending to equal to 1. So x by y equal to 1, or when r equal to 0, so when we put r equal to 0 here, we have x by y equal to 1. So when r equal to 0, we have x by y equal to 1. So for the lower values of r, x by y is approximately 1 irrespective of any damping value. So for all the curves start with x by y equal to 1, and when r is much greater than 1, so x by y is tending to 0. We can see from this frequency response curve, and we can see that here all the curves, they start from 1 at r equal to 0, start from 1. At near the resonance, they get the larger magnitude, then they are again coming down and passing through, all the curves again pass through r equal to under root 2 with the unity x by y equal to 1, and then when r is very large, they all the curves are tending to 0 amplitude. Okay. For higher value of, we can see that for higher value of r, the lower damping values give they are reaching to x by y equal to 0 faster than higher damping. So what we have derived x, that is for the absolute amplitude of mass. Now we can take another case of relative amplitude. So relative amplitude means the motion of mass with respect to the support, because the mass is on the support. So what is the relative motion of mass? So we can here take some case. So let's assume so the relative amplitude. So let's assume that z equal to x minus y. So it means that z double dot equal to x double dot minus y double dot, and from here we can write x equal to y plus z and x double dot equal to y double dot plus z double dot. So we put these values in this equation, the equation of motion. So we can have m x double dot. So x double dot we can write y double dot plus z double dot equal to minus c x dot minus, so here x dot minus y dot we can write c z dot minus k x minus y we can write z. So here we can write m z double dot plus c z dot plus k z equal to minus m y double dot. Now what is y double dot? So we can do one more differentiation here of y dot. So we will get minus omega square y into sine omega t. So we can put here minus m into minus omega square y sine omega t. So we will get m y omega square sine omega t, and this is m z double dot plus c z plus k z. So from here we can again compare it with m z double dot plus c z dot plus k z equal to f0 sine omega t, and here we can find the z equal to f0, so upon k minus m omega square whole square plus c omega whole square under root. So here f0 is my into omega square, and here we take k outside, so we will have 1 minus m omega square by k whole square plus c omega by k whole square under root. We can write z by y equal to, so here omega square upon m by k, so or k by m, so it is omega n square upon root 1 minus, so here omega square by omega n square whole square plus 2 here zeta into omega by omega n whole square. So we can write here z by y equal to, so omega by omega n is the frequency ratio r, so we can write r square upon 1 minus r square whole square plus 2 zeta r whole square. Okay, so this is the this, and here the phi, the phase we can have the we can get the similar way. So we see that we have got the here the amplitude of relative amplitude of the mass, and this is z by y equal to r square by root 1 minus r square whole square plus 2 zeta r whole square under root. So we can see this plot of the relative amplitude versus frequency ratio, and we see that this curve start from 0, this curve start from 0, so here, because when we put r equal to 0 it is 0, so it start from 0, it reaches to reaching to towards maximum values near resonance, and then it is when r is increasing it is tending towards z equal to 1. Okay, so the relative amplitude of the mass and ratio with the support amplitude, support excitation amplitude, that is tending to 1 when it is approaching to larger values of this r. Now we will do one problem based on this concept that we discussed. So here we can see the numerical this example. So the springs of an automobile trailer are compressed 0.1 meter under its own weight. So we have a automobile carrier or automobile trailer. So it is moving. It has some springs, maybe suspension springs, and they are compressed 0.1 meter under its own weight. Find the critical speed when the trailer is traveling over a road with the profile approximated by a sine wave of amplitude 0.08 meter, so and wavelength of 14 meter. So this trailer is moving on certain road with profiles of sine curve, and the amplitude is given 0.08 meter of that road profile, and wavelength is given. Now it is asked that what is the critical speed, okay, and then what will be the amplitude of vibration at 60 km per hour. So again it is asked that if it moves at 60 km per hour, what will be the amplitude. So now how this problem is related to the support excitation, because this vehicle is passing on a road that has some harmonic profile. So when it is passing on that, it will be subjected to some harmonic motions, okay, on the tire, and this will affect its vibration behavior, and therefore it is the case of the support excitation. Now here it is asked what is find the critical speed. So how the critical speed, what will be the critical speed, how we will find the critical speed. So when we say critical speed, usually when we talk in terms of frequencies, we say that when the natural frequency of the system is near to the excitation frequency, it is the critical condition. So if our road profile from the support, some excitation is coming as y sin omega t, so omega is the excitation frequency, and our system has some mass and stiffness, so it has the natural frequency omega n equal to root k by m, and when the omega is equal to omega n, this is the critical condition, and the speed that we will get under this condition will be the critical speed. So let's solve this problem. So here it is said that we have some here is our trailer, okay, and it is said that due to its own mass, that is mg, it is some compression of delta st. So you know that stiffness k equal to mg by delta st, because this is the force, the weight, and this is the deflection due to its weight. So this will give the stiffness of this spring, and then what is the natural frequency? Omega n equal to root k by m, and we can write here k into g by m into g, and then we can write k into g by m into g. M into g is k into delta st, so k into delta st. So we will get here g by delta st. Okay. And here delta st is given. Delta st, that is static. It is static deflection due to its own weight, that is 0.1 meter. So it is 0.1 meter. Now we put in this equation, so we will get g equal to, we take 9.8 meter per second square, the acceleration, gravitational acceleration, and delta st is 0.1. So we can calculate omega n. So we can calculate omega n. So it is 9.8 by 0.1. So it is coming to be 9.9. So it is 9.9 radian per second, and f natural frequency fn equal to omega n upon 2 pi, so equal to 1.57 hertz or so. So we have got the natural frequency. Now this trailer, now it is, so this trailer is now moving on a road profile. So let's say we have some road profile that is harmonic. Okay. So this is the road profile on which this trailer is moving. It has now we know the stiffness of this trailer. Okay, and this road profile is like a sine curve, similar to sine curve with of amplitude 0.08. So it means that we have, so this is 0.08 meter and wavelength is 14 meters. So this is the wavelength. So either two peaks or this. So this is lambda, that is wavelength, equal to 14 meter. Now, so what will be the excitation that is going from the support? So we know that frequency equal to the speed upon wavelength. So let's say speed is v and wavelength is 14. So this is the frequency f. Now in the critical condition omega equal to omega n or f equal to fn. So this is your excitation frequency f, and you know the amplitude 0.08. So here v by 14 equal to your fn, we have already calculated 1.57. So we can get here v so that is 22.06 meter per second. Okay. Now what will be the amplitude of vibration at 60 km per hour? So we want to know the x so we know that this we have this equation, and here we assume zeta equal to 0 because we are not given any value of zeta. So we assume it. So when we put zeta equal to 0, we will get 1 by 1 minus r square. So we have to get at first the omega when our speed is 60 km per hour. So v equal to 60 km per hour. We can convert it into meter per second. So that is 16.67 meter per second. So at this speed v by 14, so we have f equal to v by 14, so 16.67 by 14. We have 1.19, and we can get r equal to f upon fn or omega by omega n. So this is 1.19 and Fn is 1.57. So it is 0.76. This we can put here. So x upon y we have 0.08, 1 upon 1 minus r square, or 0.76 square. This implies x so it is 0.188 meter, so or 18.8 centimeter. So this is the absolute amplitude of the the vibration of the trailer when it will move at v equal to 60 kilometer, speed of 60 kilometer per hour. So we understand that how we can apply this theory of support excitation in our practical systems, and we applied here on some vehicle moving on a harmonic road profile. So I would like to thank you for attending this class, and let's see in the next lecture. Thank you.